Hello everyone. So today we are going to be studying the chapter phenols. So it is a very important chapter. It is actually a part of alcohols, phenols and ethers, but we are going to be studying this separately. So yeah, let's get started. So first we need to know what is phenol. So as you can see, I have drawn the structure of phenol over here. So when an OH group, a hydroxyl group, is directly attached to the benzene ring, then the compound is known as phenol. So in case of phenol, the oxygen atom is attached to an sp2 hybridized carbon atom, right? So oxygen is attached to sp2 carbon because there is a carbon-carbon double bond over here, and all the carbons in benzene are sp2 hybridized. So the oxygen is attached to an sp2 hybridized carbon. So an important property of phenol is resonance. So we all know what is resonance. We have done it in class 11. So this is phenol. We can also write it like this, right? So the lone pair of oxygen can resonate with the benzene ring. So it donates its lone pair. So this pi bond moves. We get the first resonating structure or the canonical form. The negative charge is over here. We get a positive charge on oxygen and a double bond over here. The positive charge on oxygen is due to the fact that oxygen has donated its lone pair. So a formal positive charge is formed on oxygen. Now this will again resonate. Negative charge is over here, two pi bonds, and this. Now this negative charge can again resonate. I'm drawing it over here. You can see, yeah. So negative charge is now over here. Pi bond is over here. Another pi bond. OH positive. Again, it will resonate, and finally we get phenol again. So this is the resonance taking place in phenol. So an important thing which we observe over here is that the negative charge is being formed on the ortho para ortho position. So this is the ortho position, this is the hydroxyl group, so this is the ortho position, meta position, para position. Again, ortho position, meta position, para position. So the negative charge is being formed on the ortho and the para position. So if we have an electrophile E positive, we know that an electrophile attacks at sites where the electron density is considerably high. So a negative charge has a considerably high electron density. So an electrophile will always attack on this negative charge. That means in case of electrophilic aromatic substitution reactions, where an electrophile attacks on the benzene ring, phenol will always direct the electrophile to the ortho para ortho positions. And why is that so? Because yes, there's a negative charge over here, so the electrophile will attack on the negative charge and not anywhere else. So phenol, it has a plus R effect. Plus R effect means it pushes electrons or releases electrons in the benzene ring. Okay, so as a consequence of this plus R effect, the electrophile will always attack at the ortho para ortho position. So this was all about the resonance in phenol. Now let's move on to an important question, which is quite common. That is, you have to compare the acidity of phenol and an alcohol. So, we know that alcohols, ROH, so they show an acidic nature and they dissociate into RO minus and H plus, right? And phenol, phenol can also dissociate into minus and H plus because it has the oxygen hydrogen bond. We know that this is known as alkoxide and this is phenoxide. Now you have to compare the acidity of alcohol and phenol. So how will we do that? We know that the acidity of any organic compound depends on the stability of its conjugate base. So in this case, the conjugate base is RO minus, and in this case, the conjugate base is phenoxide. So a quick revision for the people who have forgotten what a conjugate base is. So if a compound which is acidic, it will always dissociate into a conjugate base Cb and H plus. So if the conjugate base is stable, it is an anion actually. So if the conjugate base is stable, then the equilibrium will be shifted towards the right to a greater extent and more H plus will be furnished. Because if the equilibrium is shifted towards the right due to increasing stability of the conjugate base, then the concentration of the products, that is the H plus, will increase and the acidic nature will increase. So if we can determine that which of the following between RO minus and phenoxide is more stable as a conjugate base, then we can easily determine the acidity of phenol and then alcohol. So let's see which of them are stable. So first, let's take alkoxide. So alkoxide, it has an alkyl group over here. It can be ethyl, methyl, propyl, anything, and a negative charge on oxygen. Now we know that according to general organic chemistry, the negative charge or a carbon ion, in this case it is not a carbon ion though, it is a negative charge on oxygen. A negative charge is always destabilized by alkyl groups. And why is that so? Because alkyl groups have plus I effect. So plus I effect, inductive effect. So if a particular group has a plus I effect, it will push the electrons more towards the negative charge, and so the electron density on the negative charge will increase, and this will be destabilized. So RO minus is clearly not that stable. Now let's take phenoxide into account. So phenoxide is stabilized by resonance. Okay, so negative charge is delocalized in the benzene ring, and we know that resonance always confers stability upon any molecule. So in phenoxide, resonance is there, so stability is there. Now I'm not drawing the resonating structures of phenoxide, that you should do because I've already shown you that of phenol, and yes, that's probably your homework, so do that. So as I was saying, the phenoxide has resonance and so it is stable. So just how I mentioned that stability of the conjugate base will determine the acidic strength. So since phenoxide is more acidic than phenol, I'm sorry, since phenoxide is more acidic than than alkoxide ion, so phenol is a stronger acid than any alcohol. Ethanol, methanol, propanol, any alcohol is always a weaker acid than phenol. because the conjugate base of phenol, that is phenoxide, is resonance stabilized, and the conjugate base of any alcohol, that is the alkoxide, it can be ethoxide, methoxide, anything, so that is not resonance stabilized. Instead, it is destabilized by the plus I effect and also hyperconjugation of the alkyl group, and so the phenol is definitely more acidic. Now let's move on to another important thing, acidic nature. So just as I mentioned right now, that phenols are considerably acidic. They are more acidic than alcohols. So there are two main tests for the acidic strength of phenol. We know that in inorganic chemistry we have studied that any acid always reacts with a base to form a salt and water. So that is basically the uh, most important property of an acid. That is what determines its acidity. So acid plus alkali gives salt and water. It's a very basic thing. So if we can show that phenol also reacts with an alkali to form a salt and water, then we can prove that phenol is acidic. So there may be questions like this that prove that phenol is acidic. So in that case, we can use this, but the more appropriate one is not this. The more appropriate one is, we also know that acids will react with active metals to give salt and liberate hydrogen gas. This is also a very important property of inorganic acids. So if we can show that phenol follows these two conditions, then we can show that phenol is acidic. So let's see if phenol is acidic or not. So first, phenol, we have seen that phenol reacts with 2 moles of sodium. So 2 moles of phenol will react with 2 moles of sodium to form this compound and hydrogen gas. So here there will be another 2. So 2 moles of phenol is reacting with an active metal. So sodium is an active metal. To give a salt, the name of the salt is sodium phenoxide. So how is the name coming? So we know that this O minus is the phenoxide ion, and so if Na plus forms an ionic bond with the O minus, then it is known as sodium phenoxide. For example, sodium chloride. So Cl minus forms an ionic bond with sodium, so it's known as sodium chloride. Similarly, if phenoxides form an ionic bond with sodium, it is known as sodium phenoxide. It's simple as that. And hydrogen gas is liberated, right? So this test is confirmed. So phenols are definitely acidic. So another reaction is there to prove that phenol will react with NaOH. So NaOH is an alkali. NaOH is an alkali to give sodium phenoxide and water. So so phenol will react with sodium hydroxide to give sodium phenoxide and water. So this is just the same. So acid, which is phenol, reacts with an alkali, which is sodium hydroxide, to give a salt, which is sodium phenoxide and water. So this also proves the acidic nature of phenol. So we can say that phenols are definitely acidic. So if you are asked that prove that phenols are acidic, then you have to show these two reactions. Next is another important thing which I've already learned. It's hydrogen bonding. So phenol can form hydrogen bonding. It forms intermolecular hydrogen bonding. How is that so? Let's see. So the condition for hydrogen bonding that we have already discussed is that the hydrogen must be attached to a very electronegative atom like fluorine, oxygen, and nitrogen. So in phenol, the hydrogen is attached to an electronegative element like oxygen. So it obviously has to display hydrogen bonding, and it will be an intermolecular hydrogen bonding. There will be a force of attraction between these two, and so intermolecular hydrogen bondings will form. Okay, now we have to determine another important thing, that is solubility. So if a compound has to be soluble in water, then what is going to happen is that it should form hydrogen bonds with water. That is the criteria for an organic compound or a non-polar compound to be soluble in water. So you can obviously see that phenol does form hydrogen bonds. So it can also form hydrogen bonds with water. So it is definitely soluble in water. But due to the presence of the bulkier benzene ring, the hydrocarbon part, which is hydrophobic, which means that this part is not soluble in water, only this OH part is soluble in water. So this aryl group or the benzene group, this is a very large group, and the hydrophobic part is also very large. So due to the bulkier benzene ring, the solubility of phenol in water is less. It is not that less, but it is not that high also because of the presence of the bulkier benzene ring. But yeah, it can definitely form hydrogen bonds with water, and so definitely is soluble in water to some extent, but not to a higher extent due to the presence of the bulkier benzene ring. As the hydrophobic part increases, the molecular mass of the hydrophobic part increases, so the solubility in water decreases. So now let's move on to the preparation. So how do we prepare phenol? So there are a number of ways in which you can prepare phenol. The first one I'm going to show is from salicylic acid. So salicylic acid, this is salicylic acid, or you can also write it like this. It's the same. So it is, this compound is known as salicylic acid. Okay. So we can see that salicylic acid has a phenolic group over here and the carboxylic group.